The structure and interpretation of computer programs, bite size. 1.2.1 Linear Recursion and Iteration. Figure 1.3 A linear recursive process for computing 6 factorial. So factorial of 6 is multiplying 6 and the factorial of 5. Factorial of 5 is multiplying 5 and the factorial of 4, which is multiplying 4 and the factorial of 3, which is multiplying 3 and the factorial of 2, which is multiplying 2 and the factorial of 1, and then it ends up being 2 and 1. And then you kind of go back through and it says, okay, so then that's 3 multiplied by 2, which is ending up being 4 multiplied by 6, which is ending up being 5 multiplied by 24. And then it's 6 multiplied by 120, which gives us 720. We begin by considering the factorial function defined by n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times n minus etc. times 2 times 1. There are many ways to compute factorials. One way is to make use of the observation that n factorial is equal to n times n minus 1 factorial for any positive integer n. So, n factorial is equal to n times n minus 1, n minus 2, 3, 2, 1, etc. is equal to n times n minus 1 factorial. Thus, we can compute n factorial by computing n minus 1 factorial and multiplying the result by n. If we add the stipulation that 1 factorial is equal to 1, this observation translates directly into a procedure. So we can do this, which is define the procedure to be the factorial of n. Define the procedure factorial that takes n as input, and the body is if n is equal to 1, then we return 1. Otherwise, we multiply n times the factorial of n minus 1. And we get this to be factorial. Now let's, we can use the substitution model of section 1.1.5 to watch this procedure in action computing 6 factorial as shown in figure 1.3. So, this. Now let's take a different perspective on computing factorials. We could describe a rule for computing n factorial by specifying that we first multiply 1 by 2, then multiply the result by 3, then by 4, and so on until we reach n. More formally, we maintain a running product together with a counter that counts from 1 up to n. We can describe the computation by saying the counter and the product simultaneously change from one step to the next according to the rule product is the counter times the counter is the counter plus 1, and stipulating that n factorial is the value of the product when the counter exceeds n. Figure 1.4, a linear iterative process for computing n. So the factorial of 6, the factorial iter is 1, 1, and 6. Then it ends up being 1, 2, and 6. Then it ends up being 2, 3, and 6. Then 6, 4, and 6. Then 24, 5, and 6. Then 126, and 6. 720, 7, and 6. And this one's greater, so we stop, and it's 720. Again, we can recast our description as a procedure for computing factorials. Let's see if I can just do it this way. Okay. Cool. So, define the factorial of n to be define the procedure the factorial of n, which is in the body the fact iter, which takes 1, 1, and n as input, and then define fact iter to be the product, the counter, and max count as input. So the procedure that takes the product, the counter, and the max count as input. If the counter is greater than the max count, then you return the product. If not, then you go to fact iter is equal to, you do the fact iter times the counter and product, and you multiply the counter and product, and then you add 1 to the counter, and then you pass those through as the product and counter for the fact iter thing, and then max count stays the same. As before, we can use the substitution model to visualize the process of computing 6 factorial as shown in figure 1.4. Compare the two processes. From one point of view, they seem hardly different at all. Both compute the same mathematical function on the same domain, and each requires a number of steps proportional to n to compute n factorial. Indeed, both processes even carry out the same sequence of multiplications, obtaining the same sequence of partial products. On the other hand, when we consider the shapes of the two processes, we find that they evolve quite differently. Consider the first process. The substitution model reveals a shape of expansion followed by contraction, indicated by the arrow in figure 1.3. The expansion occurs as the process builds up a chain of deferred operations, in this case a chain of multiplications. The contraction occurs as operations are actually performed. This type of process, characterized by a chain of deferred operations, is called a recursive process. Carrying out this process requires that the interpreter keep track of the operations to be performed later on. In the computation of n factorial, the length of the chain of deferred multiplications, hence the amount of information needed to keep track of it, grows linearly with n and is proportional to n, just like the number of steps. Such a process is called a linear recursive process. By contrast, the second process does not grow and shrink. At each step, all we need to keep track of for any n are the current values of the variables product, counter, and max count. We call this an iterative process. In general, an iterative process is one whose state can be summarized by a fixed number of state variables, together with a fixed rule that describes how the state variables should be updated as the process moves from state to state, and an optional end test that specifies conditions under which the process should terminate. In computing n factorial, the number of steps required grows linearly with n. Such a process is called a linear iterative process. The contrast between the two processes can be seen in another way. In the iterative case, the program variables provide a complete description of the state of the process at any point. If we stop the computation between steps, all we would need to do to resume the computation is to supply the interpreter with the values of the 3 program variables. Not so with the recursive process. In this case, there is some additional hidden information maintained by the interpreter and not contained in the program variables, which indicates where the process is in negotiating the chain of deferred operations. The longer the chain, the more information must be maintained. In contrasting iteration and recursion, we must be careful not to confuse the notion of a recursive process with the notion of a recursive procedure. When we describe a procedure as recursive, we are referring to the syntactic fact that the procedure definition refers either directly or indirectly to the procedure itself. But when we describe a process as following a pattern that is, say, linearly recursive, we are speaking about how the process evolves, not about the syntax of how a procedure is written. It may seem disturbing that we refer to a recursive procedure such as fact-iter as generating an iterative process. However, the process really is iterative. Its state is captured completely by its 3 state variables, and an interpreter need keep track only of the 3 variables in order to execute the process. One reason that the distinction between process and procedure may be confusing is that most implementation of common languages, including Ada, Pascal, and C, are designed in such a way that the interpretation of any recursive procedure consumes an amount of memory that grows with the number of procedure calls, even when the process described is in principle iterative. As a consequence, these languages can describe iterative processes only by resorting to special purpose looping constructs, such as do, repeat, until, till, for, and while. The implementation of scheme we shall consider in Chapter 5 does not share this defect. It will execute an iterative process in constant space, even if the iterative process is described by a recursive procedure. An implementation with this property is called tail recursive. With a tail recursive implementation, iteration can be expressed using only the procedure call mechanism, so that special iteration contracts are useful only as syntactic sugar.